वेलकम टू द नेक्स्ट लेक्चर। इस लेक्चर में हम चेन रूल का एक प्रूफ देंगे। लेट मी फर्स्ट रिकॉल व्हाट chain rule is, as I have already written the statement of chain rule. So here we have open set U in Rm and an open set V in Rn, and we have two functions. First function f from AU to Rn, G is a function from V to Rt, such that the image of the image fu is a subset of V. Okay, this is the condition. यह condition के बिना हम composition function और composite function define नहीं कर सकते. Without this condition we cannot define composite function or composition. Okay. Let x be any point in U. Assume that f is differentiable at x and g is differentiable at point fx. Then the composition function GOF, okay, composite function GOF is differentiable at x, and the derivative of that composite function at point x is given by this formula. So dg of fx is dgfx dot dfx. Okay. अब इसका प्रूफ हम देखते हैं कैसे प्रूफ करेंगे. सो हमें दिया है कि फंक्शन f और फंक्शन g डिफरेंशिएबल है. सो फंक्शन f डिफरेंशिएबल है पॉइंट x पर. इसका मतलब है कि हमें एक लीनियर ट्रांसफॉर्मेशन मिलेगा. ओके, जो कि डिफरेंशिएबिलिटी की डेफिनेशन को सेटिस्फाई करेगा. हम उस लीनियर ट्रांसफॉर्मेशन को, जिसे हम df(x) लिखते हैं. Okay, dfx means derivative of f at point x. Let us denote this by L. Okay, let L be this, and let us denote dg at fx. This is by m. So here L and m are linear transformation. L is a linear transformation from Rm to Rn. Okay, and m is a linear transformation from Rn to Rd. ठीक है. ये हम जानते हैं क्योंकि डेरिवेटिव ऑफ फंक्शन इज गिवन बाय ए लीनियर ट्रांसफॉर्मेशन. उस लीनियर ट्रांसफॉर्मेशन को हम L और M से डिनोट कर रहे हैं. What this theorem asserts is that, okay, let me write what the theorem asserts is that GOF is differentiable at the point x, and its derivative is the linear transformation or linear map M of L, MOL. Okay, the composite map, which is defined from Rn to Rm to Rd. Okay, so you see, from Rm to Rn you have this linear transformation, then here you have Rd. So composition M of L is from Rm to Rd. This is what we have to show. Okay, at the beginning, let me set y equal to fx. So now we use definition of derivative. By the definition of derivative, f is so it is given that f is differentiable at point x. This means fx plus h equal to fx plus L of h plus mod h r h, where limit h goes to 0, r h is 0. Similarly, g is differentiable at fx means g is differentiable at y. This means gy plus k equal to gy plus mk plus mod k. So you see I am using mod, so you may write is okay, let me write norm. Okay, norm k sk. Here again limit k goes to 0, sk is 0. Okay, this is by the definition of derivative. Now what we do, we consider GOF of x plus h minus GOF x. Correct? So what do we get? G of f x plus h minus g of fx. What is fx plus h? Fx plus h is fx plus lh plus norm h rh. So fx is y plus lh plus mod h rh, okay, minus gy. Now we can write this as gy plus k, okay, minus gy, where k is lh, let me write norm h, lh plus norm h rh. Correct? So, but what is gy plus k minus gy? Here we have gy k minus gy is mk plus norm k sk. Write that. So we get mk plus norm k sk. Okay. So what is k? K is lh plus norm h rh. So we have, as m is linear, we have mk equal to mlh plus norm h rh. This is equal to m of lh plus norm h mrh. So let me write what we have achieved so far. What we have achieved is the following: GOF x plus h minus GOF x equal to m of LH, okay, plus norm h mrh plus norm k sk. Okay, to prove our result, what we will show that this is of order h. This term is of order norm norm H. Okay. So claim is norm H MRH plus norm K SK is of order H. Okay. So for this consider this term plus norm K SK and use triangle inequality. What we get? We will get norm H. No. So from linear algebra, we know norm ST is less than equal to norm S, norm T. We will use. So this is from linear algebra. Okay. For any two linear transformation as norm of ST. So whenever we can define ST. So this means S composed T. So here what we will get norm M, norm R, norm RH plus what we get. So norm K is so let me write what is K. Uh, K is this. Okay, K is this. So this is norm LH plus norm H RH. Okay, and norm SK. Okay, let me omit this part. So what do you get from here? Here, what we get is this. Uh, this is norm H. So let me bring norm H common, then what I'll get. So wait a minute. Let me. So this is norm H, norm M, uh, norm RH plus this is so again from linear algebra norm Tx is less than equal to norm T norm X. Okay, we will use this. So this is norm L and norm H plus norm H, norm RH, norm SK. Good. So we will take norm H out, and what we get is norm M, norm RH plus norm L plus norm RH, norm SK. Okay. Now, as limit h goes to 0, k, this is go to 0. Okay. Why? So this is limit. What is k? K is LH plus norm H RH. Okay. So L is a linear transformation. L is a linear transformation from Rm to Rn. Since L is a linear transformation. Okay, so LH will go to L0, that is 0 as H goes to 0. And we already know as limit H goes to 0, RH is 0. So this means this is 0. Correct? Okay, and we know as k goes to 0, Sk is 0. This implies limit H goes to 0, Sk is 0. Okay? So this means this implies what we get is the following. We get GOF x plus h minus GOF x this equal to let me see above, this equal to m of LH plus O norm h. This means GOF is differentiable at x. Differentiable at x, and the derivative is given by, and the derivative is given by the okay, or let me write derivative at x is given, derivative of GOF at x is given by the linear transformation M of L. Okay, so this means DGOF x equal to M of L. Or what does this mean? GOFX means what was M? We have already defined M. M was D G of Fx, and what was L? L was D of Fx. So we get the final relation or final result. So here is the proof. This is the end of the proof. So now we see a consequence of chain rule. A consequence. As an application of chain rule, what we now do, we will consider the problem of differentiating an inverse function if inverse exists. Okay. As an application of the chain rule, we consider the problem of differentiating an inverse function. Inverse function if exists. Okay, we assume that the inverse function of a function exists, then and the function given function is differentiable, then how do we differentiate the inverse function of given function? Okay, so recall this situation in single variable. So recall that in one variable, real analysis, suppose phi is okay, phi x is a okay, let me assume, suppose phi x is a differentiable function. Okay, differentiable function um, on some open interval, on some open interval with the condition that phi dash x is strictly positive. What does this mean? This means phi is strictly increasing. Okay, this means phi is strictly increasing. Correct? So since this is strictly increasing, this means this function is 1 1. So phi is that is let me write this implies phi is 1 1. Phi is a 1 to 1 function. Okay, 1 1 on the interval, on the given interval. Okay, so if phi is defined from I to phi I, then we can talk about its inverse function, psi. Okay, suppose psi is the inverse function of phi. Okay, psi is given from phi I to I. Correct. Here, psi of phi is identity function, and similarly, phi of psi is also identity function. Okay. Correct. This then this inverse function is defined, and if if phi is differentiable, if phi is differentiable on I, then psi is also differentiable. Psi is differentiable, and it satisfies the following things: psi dash y equal to 1 by phi dash x, where y equal to phi x. Okay, so this is how you differentiate inverse function in one variable. So there is a similar formula for differentiating the inverse function. Let me write that. There is a similar formula for differentiating the inverse of a function f of several variables. Okay, so here I am saying inverse of a function f of several variable if inverse exists. Okay, if inverse exists. So so provided it exists. So we are not considering here the question whether the function f has an inverse or whether that function is differentiable. We are not saying that. So if function is if inverse function is exists, okay, and that is differentiable, how do we compute differentiable derivative of that function? This is our aim. ओके, क्या एम है? एक फंक्शन दिया हुआ है सेवरल वेरिएबल का जिसका इनवर्स एग्जिस्ट करता है और वह इनवर्स फंक्शन डिफरेंशिएबल है, तो उसका डेरिवेटिव हम कैसे निकालेंगे, यह हमारा क्वेश्चन है. सो फॉर दैट वी हैव द फॉलोइंग थ्योरम which is a consequence of chain rule. Let A be open in Rn Let f be a function from a to Rn. Okay. Let fa equal to b. Suppose that G maps a neighborhood of B into Rn, and suppose that GB equal to A, and G of fx equal to x for all x in a neighborhood of A. If f is differentiable at A, and if G is differentiable, we are saying G is also differentiable. Okay. If f and G both are differentiable at A and B respectively, then the derivative of this function G at point B is given by inverse of DFA. Okay, you know this DFA is a matrix, and DGB is inverse of that matrix. So proof is very easy. Proof. Okay, F and G are inverse of each other. Okay, so you see, so see here, what is G of fx? This is given by x, means G of f is the identity function. Okay, so let me take identity from Rn to Rn. This be given, let this be identity function. Okay, be the identity function. Identity function means idx equal to x for all x in Rn. Okay, then what is D of this identity function? This is identity matrix. Okay, this is the identity matrix of order n cross n. Identity matrix of order n cross n. Okay, so here what we have G of fx equal to x for all x, and this is nothing but identity of x. Okay, for all x in so in a neighborhood of small a, for all x in a neighborhood of a. Okay, in some neighborhood. Now we apply chain rule. Chain rule implies that d of g of fa is d of g of fa dot d of fa. Okay, but what is GOFA? GOFA is identity. This is D of IDA. Okay, but what is this? This is identity matrix. This is the identity matrix. Correct? So what we get? We get DGFA dot DFA is the identity matrix. So from here, what we get? DGB is DFA inverse. So this is the proof, a very simple proof. Okay, so what we have seen today, we have seen a proof of chain rule and a consequence of chain rule. Okay, so let me stop here.